And here interference between fuselage and the tail wing. Okay, so this curve is for only the tail wing. Okay, and this curve is for the fuselage plus tail. Okay, so if you take tail alone, you can see approximately around 12 degrees, the CL is of 0.7. Okay, but if you include the fuselage in the tail, so here for 12 degrees, the CL is around 0.35 or something. Okay, so because of this fuselage, there is a disturbance flow that reduces the lift off and tail. Okay, from 0.7 to 0.35, around 50% it reduced. Okay, so like that, the interference is reducing the lift on the tail. You can see the disturbed flow, how it flows on the tail. Okay, so the disturbed flow disturbs the both main wing flow, also the tail wing flow. But compared to the main wing, tail wing, it will experience lot of disturbance. Okay, here also you can see the flow is up to this, it is somehow attached, but from here onwards it is separating. So the full separated flow affects the tail wing. So compared to the main wing, tail will experience lot of drag. That is a lot of disturbance compared to the main wing. And here I explain fuselage wing disturbance. So here I explain high wing, then mid wing, then mid wing, then low wing. Okay, how the drag increases for low wing, mid wing, and high wing. So only one parameter. So always we have to be careful that the flow should not be disturbed on the upper surface. Okay, lower surface if you take, it will be a high pressure region. Okay, even if you disturb also, so we can compensate. But upper surface, most of the flow changes occurs, and we have to get the maximum acceleration and low pressure region. So the upper surface flow should not be disturbed. That is the main thing. So if you take this upper surface, that is a high wing, you can see all this disturbed flow almost in the bottom surface only. The upper surface is very less disturbed. So this produces minimum drag. The high wing configuration produces minimum drag. So this blue color is only for the wing, and this red color is for the wing plus fuselage combination. You can see for the high wing configuration, the drag is increased, but at least the trend is same. Okay, the trend is same for wing alone and wing plus fuselage configuration. If you take the high wing, because most of the flow disturbance happens in the lower surface, upper surface is less disturbed. But in the mid wing, if you take, the disturbed flow will be both are upper and lower surface. So here you can see up to 12 degrees, there is a little bit increase, but it follows the trend. After that, there is a drastic increase in drag, because at high angle, there will be a lot of disturbed flow over the wing. Okay, so at high angle, the drag is increased drastically for the mid wing configuration, because half of the disturbed flow is going on the wing. And if you go for the low wing, you know, almost all the disturbed flow will be there on the upper surface. So here you can see from 6 degrees itself, the drag is increasing. Okay, at least in the mid wing, from 12, the drag is increasing. Sorry. From 12, the drag is increasing for the mid wing. For the low wing, from 6 degrees onwards, the drag is increasing. So now if you compare these three configurations, high wing only produces minimum drag. But if you go for designing of aircraft, we don't see only the aerodynamic properties. We have to see structural consideration, economical consideration, everything we have to take it, even performance parameters. So if you go for the high wing, the drawbacks are the structure beneath this wing should be very strong to withstand the wing weight. Okay, so we have to add more structure, that means more weight. So unnecessarily it increases the complexity. Okay, unnecessarily we are increasing the weight also. So mostly we are not going for the high wing. High wing configurations only we will go for the cargo type. Okay, because cargo means the total weight will be very high. Then to withstand that, we have to produce more lift. So the wing span, wing area, everything will be very high. Also, it has to withstand a heavier engine. Okay, so we need the better clearance from ground to the engines, all those things. So for the cargo type heavier aircraft, we are going for the high wing. Almost all other commercial aircraft, we are going for the low wing only. You can ask, sir, the drag is more, why we are going for low wing? At least you can go for the mid wing. So this is first thing. If you go for the high wing, weight, structural complication, everything will be more if you go for the high wing. And if you go for the mid wing, even though the drag is less, at least up to 12 degree, what will happen? All those spars, the spar means the main structural element of the wing, that will be crosses through the fuselage. Okay, so we cannot use fuselage space in between this region. We know the main purpose of the aircraft is to accommodate more passengers and it should be economical. Okay, we don't see only the aerodynamic parameters. So if you go for the mid wing, all those main elements of spars and all, it passes through the fuselage. So this area cannot be used. So practically it is not feasible. So we are not going for the mid wing also. So mostly we are going for the low wing. Okay, so it is easy to attach it. All those parts can be passes through the lower surface, so the fuselage is not affected. So for this manufacturing, other structural consideration, we are going for low wing, but this produces high drag compared to the mid wing and high wing. Is that clear?
Yes, sir.
Okay. And here, position of wing in the axial direction or longitudinal direction. So from nose to towards the tail, they are moving at. And you know, if it is near the nose, the disturbance will be less. So definitely this will produce minimum drag. And if you move in this direction, definitely disturbance flow will also be high. So drag will be high. That is very clear. Here also you can see for first configuration, it is almost, that is, so this line is only for the wing. Okay, the bottom line. And all other lines are for wing plus fuselage combination. Okay, if the wing is placed near to the nose, the disturbance is less, so the line is almost parallel to the first configuration, wing alone configuration. For other configuration, you can see the drag is increasing for the lower angle itself. But we know practically we cannot go for this nose attachment because there will be a cockpit, there will be other electronics item, everything will be there. So we cannot place it there. It will be placed behind the cockpit. Okay, even though so maybe it will be equal to these two configurations, right? So we don't see only electronic properties, other arrangement also we have to see. So there will be all the electronic equipments, those things and all, so we cannot place it here. It will be next to the cockpit. Then next one, tail configuration. A different tail I shown, V tail, conventional, cruciform, touch tail. I don't know the name of this. So different configurations are there. So here the key point is, if the joints are more, drag also will be more. Okay, because for every joints and corners, there will be eddies. Okay, there will be disturbed flows, eddies, that increases the drag. That is the main key point here. Okay, if the joints and corners are more, drag also will be more. Now you can see compared to this configuration, this V tail has the less joints. Okay, here only 2 joints. Here 3 joints and corners. If you see 1, 2, 3, 4, 5, 6 corners. Okay, like that. Here it is further increased. Here it is further increased. Here 1, 2, 3, 4, 5, 6, 7, 8 corners. Here it is around 12 corners, I think. So joints and corners are increases, drag also increases. You can see 0.2, 0.3, 0.38, 0.48, 0.76. Either the drag is increasing. And if you come to the commercial aircraft, actually this produces minimum drag, but we don't use this for the commercial aircraft because the control stability and all, it is difficult. You know the name of the control surface used in the V tail, right? What is the name? What is the name of this control surface used in the V tail? Anybody? Are you there? Hello? No connectivity issue, right?
Yes, sir.
Okay. Elevator. You could answer, right? Elevator. Okay. So in the conventional, we call this as rudder, right? This is rudder, this is elevator, right? Conventional configuration. But in the V-tail, there is no separate rudder and elevator. Okay, we have only one control surface that is called rudder waiter. Okay, rudder waiter. Combination of both rudder plus elevator. So in the conventional type, if you take, there is separate control stick for the rudder and elevator. So for the pilot, it is easy to control. But in this rudder waiter, simultaneously you have to control both this rudder waiter, that is angle, etc. And you have to change it to do the maneuvers. So the controlling is difficult if you use the rudder waiter. So even though the drag is less, we don't go for the V tail because there is only one control surface that is called rudder waiter. So the control stability is difficult for the pilot. So we don't go for the rudder V tail. We go for the conventional. Even though the drag is little bit higher, the control stability is higher here. Only for the UAV and the smaller configuration, smaller aircraft configuration, we go for the V tail. Is that clear?
Yes, sir.
Okay. And here I said, if there is a sharp corner, there is a eddy, disturbed flow, the drag is increased 3.3. So the way to reduce this drag is to give the edge fillets. Okay, it can be the convex or concave shape, anything. So converting the sharp corner into the smooth rounded corner, we are giving these edge fillets so that the drag can be reduced to half, 3.3 to 1.8 something. Okay. So to avoid the sharp corner, there should be edge fillet to reduce the drag. Example you can see here. In the olden aircrafts and all, almost all the wings are supported with the bracing. Okay, so a lot of corners here. So later they modified that to the edge fillet. That is, additional fairing was given so that the sharp corner is converted to the curved one, edge fillet. Like that they reduced. And nowadays we have very advanced materials and all. So wings doesn't need this additional bracing support. The wing itself can withstand its own weight. Okay, so no need of additional bracing and all nowadays, because nowadays we have a lot of fibers, composites, etc. and all. So here only we are using, instead of sharp corner, we are going for the rounded one, that is called edge fillet. And here I explain interference between fuselage and wing. So this thing already we studied. If there is no fuselage, this blue color line will be the lift distribution, and if there is a fuselage, then the lift will be reduced. Okay, near the fuselage. The lift already we studied, and the top they explain the drag distribution, how the drag curve varies. So here it is constant on both sides, and here there is a corner, so there will be eddies, so the drag is increasing in the corner region. Then the center also it is increasing, but it is not symmetrically distributed. It is like some uneven distribution, because the flow, if you see, it is a three-dimensional flow. It is not just 2D. Okay, in the real condition, the flow is 3D. It is going here and there randomly. So we are getting this type of uneven distribution. Is that clear? Wing fuselage interference. Okay. Then this is wing fuel tank. In the olden aircraft and all, the smaller aircraft, the wing may not have the enough space to store the fuel. So additionally, they used to attach the fuel tanks. Maybe in the center or in the tip of the wing, they used to attach the fuel tanks. So that fuel tank, initially they attached using the just rods, bars. Okay, that is called strut. Using the strut, they attached. N number of strut will be there. So you know all the strut will act as a some cylindrical bar or some bar-like structure. So more drag will be there because of bluff body structure. So drag is 0.26. Then instead of the n number of bars, they went for the streamlined thick fairing. So the drag is reduced to 0.1. Then now we have any advanced materials. So with the thin fairing itself, we can attach the fuel tank. So it is further reduced to 0.06. Okay. Strut has, it is like a bluff body, more drag. Then streamlined thick body, 0.1. Now it is thin streamlined body, it is 0.06. Like that they reduced. and here fuselage design. So if you take fuselage alone, like a airfoil structure, then the drag is 0.15. Okay, and if we provide, there is a opening in the fuselage. Also, if you attach the pilot, then the drag is increased to 0.19. And in the same fuselage, if you provide the windshield, then it is increased to 0.23. Okay, because we know how to convert the bluff body to streamline body. We should not take care only the front portion, rear portion also important. So now even there, if you attach the engines further, then it is increased to 0.6, that is 0.59. Okay, so without engine, only the windshield, the drag is higher. And how to reduce the drag means we have to give the rear fairing. Okay, so the flow should leave the fuselage smoothly. With that, we can reduce to 0.2. Okay, so we should not take care only the what is it, front portion. Rear portion also important. So we have to give the rear streamlined fairing, so the drag can be reduced to 0.23 to 0.2. Is that clear? In the force balance, we have seen ball and the streamline structure. We should not see only the front portion. The rear portion also very important. So instead of in the ball, the drag is very high, but we converted the ball into the streamline shape, the drag is reduced. So to convert this bluff body to streamline body, rear portion also you have to take care. So rear fairing is must. Is that clear? So in the one word they may ask, so which has the less drag? Only with the front windshield or front windshield with the rear fairing. So you have to tell with rear fairing it will produce a less drag. Okay. And again, this is sharp effect. So this cockpit here it is very sharp. So drag is 0.2. If you make that as a smooth streamlined body, it is reduced to 0.04. Same concept. Here it is sharp corner, it is 0.092. Here it is a little bit smoother, 0.072. Nowadays we don't see this bulge. Everything is merged into the streamline shape, so it is reduced to 0.07. So now it is of single shape like aerofoil shape. And here they explain engine disturbance. So this is the radial engine, piston engine. So if there is no covering, there is no cowling for the engine, the drag is of 0.49. And if you give the cowling, that is covering for the engine, it is reduced to 0.25. Then engine mounting. In the olden days and all, they attach the wing, that is engine on the wing. So already I told you, we have to be careful that the flow on the upper surface is not disturbed. Okay, but here this configuration creates lot of disturbance over the upper surface. You can see this is strut. Okay, that itself acts as a bluff body. This engine is another one bluff body. So the drag is very high, 0.67. Then they removed this strut. Instead, they gone for the fairing. So with that, they reduce the drag to 0.33. Then they moved the position. So now they merged both wing and the engine. So it is little bit reduced because it is very high, very thick. Now it is the thickness is reduced on the upper surface. So the drag is further reduced to 0.2. And nowadays you can see all those engines are placed below the wing. So because now we know we should not disturb the upper surface. So all the wings are placed below the wing with a pylon, with the help of pylon. So the drag is further reduced to 0.17. Then landing gear disturbance. So if the landing gear is not retractable type, you can see how much disturbance it creates. Okay, that's why we are going for the retractable landing gear. But in the olden aircraft and all, if you see, it will be a fixed type. Okay, so in the first configuration, there are a lot of bars. Okay, the drag is 0.55. Then they removed these two bars, only two bars on one side. So the drag is reduced to 0.52. Okay, two bars and wires. So 0.52. Then here 3 bars but with the fairing on the wheel. The wheel also a bluff body. So they have given the fairing. So it reduced to 0.36. And nowadays you see there is only one strut, landing gear strut. So it is reduced to 0.25. Further, if you give the cowling that is covering for this, it may be reduced to 0.15 something. It will be further reduced. Okay. This is another one
So,
configuration. Tell me.
so can you go to the so in this won't this reduce the integrity of the strut during landing because of the impact? Having more
That's why
space would
nowadays, previously it is a only metal structure. Now we have a lot of composites. Okay, carbon composites, many things are there. So with the lightweight itself, it can withstand more weight. That is the difference between metal and the composites, right? So
yes sir.
nowadays, so previously the aircraft used to be full of metals. Nowadays, around 60 to 70 percentage, it is replaced by the carbon composites. Okay, very lightweight, but the strength will be more compared to these metals. Okay,
Okay sir.
so here also it is fixed type. The drag is 1.01, and if it is retractable, the drag is reduced to 0.51 because it is a smaller aircraft. There is no space inside the wing, so they can retract just below the wing only. It cannot be taken inside the wing, so it is 0.51. And if you give the fairing, that is thick fairing, which covers both strut and the wheel, it is further reduced to 0.28. And if you can go for the thin fairing, separate fairing for the strut and the wheel, it is further reduced to 0.21. This is almost same. So for fixed one, 1.16. If it is retracted below the wing, it is reduced to 0.66. And half of the things are taken inside the wing. So only half of the wheel is exposed to the airflow. So the drag is further reduced to 0.18. And we know how to convert block body to streamline body by giving the rear fairing. If you give the rear fairing from 0.18 to 0.08, it is reduced. Okay. And this is propeller effect. Because of the rotation of the propeller, there will be a spiral flow. Okay. For example, this is the propeller. This green color is the propeller off condition. If there is no propeller, we know we will get the symmetrical flow lift distribution on the wing. Okay. If there is no propeller, and if the propeller is added, and if it is rotating in the clockwise direction, so this side, this is how the tangential flow, tangential velocity will be acting, right? If it is rotating, so this side it is upward, this side it is downward. So this is like upwash, this is like a downwash. Now if you see, because of this upwash, the lift is increased in this region. Okay, and because of this downwash in this region, the lift is reduced. Then it follows the original lift distribution. Okay, so the blue color line is for the clockwise rotation of the propeller. So this side upwash, the lift is increased. This side like a downwash, the lift is decreased. Okay, this is for the clockwise. Now if you take the anti-clockwise, if it is rotating in the opposite direction, now here upwash, here downwash, then you will get this red color line. Okay, because of the upwash, here the lift is increased in this region, and here downwash, so the lift is decreased. Okay, so depends upon the direction of rotation. For clockwise direction, blue color. For anti-clockwise direction, red color. If there is no propeller at all, then it will be like a green color.